So another great historical example of how perception matters is a device called Canon Cat. It was a computer dedicated to one single task, the task of typing texts. So people wouldn't call it a computer, it's just a text editor, something of that sort, yeah. And it was designed by a group of people. One of them was Jeff Raskin. And he tells the story about one of its features. People thought it was very, very fast. It was indeed. It had a very interesting approach to several things. For example, if you look for pictures of Canon Cat on the internet, you will see that it has additional buttons on the keyboard called leap forward and leap backward. And there is a video in which they explain how these two buttons simplify things such as searching for a string or replacing certain pieces of text. But what I'm going to tell you about now is how they relied on this perception trick to make people believe that it's a very fast machine, when in fact it was just like any other one. This computer had a screen where you could type your text. All of the stuff was then saved to the hard drive, and that's where you would keep the files. You would load them from the drive into RAM, display, edit, and then save them back. The speed of reading and writing, so input-output on the hard disk, was not very fast. So when you press the on button to turn on the machine, it would take a while before it boots the operating system, loads your last document, displays it on the screen, and lets you do actual editing. But they leveraged the knowledge of the fact that if you look at the hard drive and you represent it as a disk, they knew that read speeds are much faster in one specific area. For example, here at the edge of the disk, or maybe in the center, I don't know. But what matters is that one of them was very, very fast, the other one was slower. So what they did is the following. Whenever you turn off the system, it takes a bitmap screenshot of the whole thing, pixel by pixel, not as text, but as just a bunch of colored dots, and saves it to this area of the drive which is read extremely fast. Now, if it's a bitmap, it's like the difference between scanning a page and having it typed. When it's typed, you can search, you can edit, you can change things in it. When it's a bitmap, well, it's just a picture. But that's good enough for what they did. So what they did is the following. When you turn it off, it takes a screenshot, saves it to the fastest area of the drive. When you press the on button, the first thing it does is it reads this easily accessible area, retrieves the bitmap from it, and draws it on the screen as a picture. By the time the person does this mental effort of thinking what the text was, what was the last thing they were thinking of, by the time the person is done, so is the computer. It has finished loading the operating system and the document, and by the time the person says, okay, I'm ready, so is the program. And you have your cursor and you can type. So what this means is that even though the computer was unable to actually edit anything for quite some time, but the screen already displayed the last document the person was working with. And this is what gave people the perception that the whole system was very, very fast, when in fact it was just like any other system from the same period. The only thing that changed is how they took into account the physical capabilities of the storage device And the fact that for a person matters to have some fast visualization on the screen. So this was done, I think, sometime in the 70s or maybe in the 80s, in the 1980s. It's a neat trick, very simple to explain.
But then the user can type on it, right?
It's just
Yeah.
momentary.
Yeah, they cannot type it as long as it's a bitmap. But remember that when you see a text, you have to remember the context. You probably need to read some parts of it to memorize what you were about to write when you turned it off. So by the time you're done with your mental process, the computer is ready to take your feedback.
So what was exactly Canon Cat? Can you explain?
Yeah, Canon Cat is the name of this device.
What does that device do? Just type?
It's a
Just a type.
text editing specialized computer for text editing. Yeah, it was designed by a group of people. Among them was Jeff Raskin, and he was also the guy who laid the foundation for the interface experience of the first Apple computer.
Apple.
So they are so cool because the people who were there in the very beginning thought a lot about things such as perception, cognition, and they established a very decent set of human interface guidelines. And once you've covered that part, others, even if they don't know psychology or human memory or human attention, they can just follow the rules. And as a result, you will obtain some pretty not bad software. That's why I told you previously that any platform that has some self-respect must have a human interface guidelines document. It should be free. You shouldn't need to pay for it. Because if programs for your operating system are cool, everybody will just keep talking about it on forums. And that's one of the reasons why Apple systems are popular. And people say, at least back in my country, it's a common thing to say, Apple computers are very good for design. How? How is it different from a non-Apple computer that runs the same Photoshop software, for example? There is no difference, but people keep retelling this myth, and the whole world lives under the impression that
under the line.
that in Apple computers there is some kind of a magic chip that gives you the power to be more creative or more productive as a graphical designer. Okay, now I will switch to the part that has implications on computer security, and I will begin with a simple exercise. I'm going to generate a sentence, such as, this is a test sentence. Can you repeat it?
This is a test sentence.
This is a test sentence.
Was it difficult to repeat it?
No.
Okay, it was easy because it was buffered in your short-term memory. It's memory that is concentrated on things that happened just a few moments ago. You can access that memory very, very fast with very little investment in terms of time, effort, etc. And if I ask you again, what's the sentence, Lynn, what are you going to tell me?
What?
Well, you weren't paying attention, most likely. Can you repeat the sentence again?
This is a test sentence.
Okay, this is a test sentence. So you can see that it persists in your memory for at least a few minutes. And when I begin throwing new stuff at you, it will probably overwrite. Now let me give you another challenge. Can you tell me the same sentence backwards?
Sentence
is
test is this.
Okay.
You missed
Yeah. Sentence
Oh,
of
you missed it.
missed it.
This is, yes.
Now let's analyze that a little bit. So in both cases you had the same number of words and the same number of characters. Let me just write it down. This is a test sentence. Wow. With this I'm going to be a doctor. Now it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it has 20 characters. Let's say it's 20 bytes. So one could argue that with your primary memory, you could memorize 20 bytes like this. But when I gave you the second challenge to read it to me backwards, you were still able to get it done, but you had a higher error rate, it took you longer, and it required a greater mental effort. So the cost of one operation was significantly larger than the cost of the previous operation. So that's one thing. Even though in both cases it was just 20 bytes. It's not that much. Now imagine that I do something else. I take the same letters from this sentence, for example, S, T, H, I, A, T, E, another E, N. So I took the same 20 bytes, but randomized them. And if I ask you to tell me this, will you be able to answer this, to deal with this challenge easily? No, because even though these are the same 20 bytes, but there is no relationship between them. There is no pattern you could rely on. There is no pattern you could leverage to simplify the problem. And what do you think is the next thing I'm going to tell you? Where this applies in computer security.
Encryption?
Yeah, it does. What's the next keyword? There is just one keyword I'm really waiting for you to tell me. What happens when you log on to some kind of service?
Authentication?
Yeah, and how is authentication implemented?
Validation.
User ID and passwords.
Okay, password.
Yeah.
That's the keyword I was waiting for. Now, passwords are like this. The same 20 bytes, but random. I mean, if we are talking about passwords which are considered strong, secure, not passwords like password or test or something of that sort. And we have just empirically established that memorizing this is much, much more difficult than memorizing that. Now, why on earth does every interface you ever lay your hands on ask you to type in a password, and it encourages you to use random characters, numbers, and punctuation marks and make it at least 8 symbols long? When what they could have done is that they could have rewritten that as enter your passphrase, where you have to enter a sentence, which is much longer. I mean, because it's made of words, and you treat them not as individual bytes, but as high-level units, it's easier for you to memorize them. Mm-hmm. This way, you could memorize a long passphrase, which would be secure, because brute forcing along a sentence is much more complicated than brute forcing a short password. So this analogy brings us to the conclusion that it is very important for people who design interfaces that have any kind of security implications. It is very important for us to know things about cognitive psychology, about memory, about forgetting, because when you know that, you can take into account such tricks. Mm-hmm. If you don't know that, then you end up forcing people memorize arbitrary sequences of numbers.
But then why do many interfaces have it that way?
Well,
like even Gmail, Google, Facebook, they don't accept. I mean, they do accept, but
they accept, but like certain they want you to have an uppercase or one
even the
lowercase.
banks and all that, they specify that you, for example, Chase Bank, they specify you shouldn't use special characters in their passwords and all that. So
Yeah, so there are multiple possible ways to answer that. One of them is because they don't know cognitive psychology. Second, because, well, it's because we've been doing this for ages. Why should it be changed?
Why should it be changed?
And to deal with this, you could take a very simple test program that runs a brute force attack against something and see how it does with a password like this versus a passphrase, which is longer. And I predict that a passphrase is going to be a better approach.
Even if it includes many special characters, symbols, and all those.
Well,
then it won't
you can include
Anything.
a comma, a dot, a space, and nobody, there is no law in the universe that prevents you from entering a $sign, for example. But still, the idea is that memorizing a sentence is a lower cognitive, places a lower cognitive stress on your mind than does memorizing a much shorter sequence of arbitrary characters and numbers. Yet people keep doing this when they could at least give a try to this. And generally, human memory is about finding patterns and regenerating content from some basic key ideas. Now imagine that I'm going to tell you to memorize the following sequence of numbers. Can you memorize it?
39.
not quickly, but
But you can.
yeah.
What if I tell you that there is a very simple rule behind this? That is the number followed by its square, next number plus its square, next number. So 3, 9, 4, 16.
525.
So now, once you know the rule,
It's easy to.
yeah, you don't have to remember the whole thing. You just need to remember the little trick. And then you can regenerate the rest from this initial information. And I can give you another example. What is your favorite song?
Oh,
One of them.
on the top of It's My Life.
By Bon Jovi?
Yeah.
Okay, tell me the 23rd word in that song.
No.
No clue. But if your life depended on it, what would you do?
I would say it in my mind and then count the 23rd.
Okay, so memory is sequential. You need to know the starting point,
Right.
and then as the story unfolds, you begin remembering the next words. So it doesn't work like, for example, an array, where I could say something like, give me the 5th element, and it gives me the 5th element. No, it doesn't work that way. It works more like a linked list, where you start with the head of the list, then you go to the next element, and then the next one, and until you reach the 27th word. In other words, it will be easier for you to remember long passphrases. And I can remember childhood stories that were read to me when I was, I don't know, 3 years old. I can still remember them, even though the last time I saw that text was 1,000 years ago. So you will be surprised that human memory can rebuild content with a pretty high degree of accuracy as long as you can give it a few starting points. And as you proceed in rebuilding the picture, new elements come to the surface, and that's how you can rebuild the bigger picture. So this is one implication. Passphrases versus passwords. If you make people memorize this, you do them a disservice. Try something like that, and it will be easier. And in fact, you probably, well, there are different sites. Some of them tell you that your password has to be at least 8 characters long and no more than 16 characters in length. But many sites don't have an upper bound on the password. So this already works. All you have to do is in that little string that says type your password, just replace password with passphrase. And most people, or at least a number of people, will be more inclined to type something like that rather than something like this. So this was an example of how knowing something about how memory works can help you make better decisions in terms of wording labels on your interface. Another thing I wish to share is an idea that occurred to me when I was watching presentations last Wednesday. It was a group of people, most of them were from China, I think, and they said that in their policy there is such a thing as telling people to lock their computers when they leave them unattended. Do you remember that?
Yeah.
Do you think this is a good policy?
Hmm?
When they to lock their computers when
Yeah.
When they move away from the desk, right?
Yeah.
It is.
Yeah, it is followed actually. Correct.
Okay, so it's a good thing to have such a feature, right? Do you think people do that?
No.
Why?
They tend to forget when they move.
Yeah, they tend to forget. So what they did in their document is they took the easy way out. They wrote something like a set of rules, and one of the rules says, you shall lock the workstation when you leave it. Now, if somebody breaks that rule, then the security supervisor drops by and says, hey, you broke rule number 3, you're out, you're fired, you're downgraded, demoted, whatever.
Rather than that, we can just automatically lock it.
Exactly. So what they did is they placed the burden on the shoulders of the human. When in fact, what they could do is that they could let the programmers think about it and come up with several different solutions. So let's enumerate them. You just told us about one of them.
So it's like to detect the presence of the person in
Well,
front of
I
you.
think
It's there in the
Yeah, it's there in-
phone in Samsung Galaxy S3. Like when you are in front of the
When
when you are
unattended.
using it, the screen glows up, and when you are not using it, automatically.
Closes the screen.
But I guess in companies also it's the
Yeah,
same
my
thing. I
computer
mean,
locks after like a
yeah,
minute
after
or
5
that's,
minutes it
uh,
locks on itself. So
Yeah, there's a timeout feature.
timeout
Okay.
feature.
So it's easier to implement a timeout
Lock.
locking feature, which completely eliminates the need of having this rule.
No, but then it times out after a while, right? If somebody wants to get into your computer, you still have a minute or two to get
Yeah, they still have a minute
Yeah.
or two.
That's the drawback. Yeah.
So it depends. In some environments, this will be a good solution.
Mhm.
In other environments, this is not good enough. You need instant locking as soon as the person walks out.
But you know, in the case in their rules, that it would be a flaw in the sense that till the time when the supervisor comes and checks, the person whoever has hacks in and he goes
That's
away.
exactly
That's
what
what
he's
he's
saying.
saying.
That's exactly
You
what
have
he's
you have 1 to 2 minutes to hack and get into the system.
If you have a timeout of 3 minutes and within
Uh-huh.
that 3 minutes or somebody comes in and just moves the mouse, that's it, the timeout is reset.
Yeah.
So he can do whatever he wants in that time.
So even though a timeout rule is a step forward,
Yeah.
it's not perfect.
Mhm.
What else can we do? From a purely engineering perspective.
Sensors. I think that would be a better way of doing it.
Yeah,
Okay.
that's also.
And when you say sensors,
He leaves his cubicle and
so you need some kind of a presence.
Physical light is still, I think, it's still applicable to most of the offices, but sensors.
Maybe like sensors in the chair, like the minute you get up,
And yes.
it senses you're not sitting in front of the PC. So
As in, a
But
sensor
what
more
if you are
connected-
working
yeah,
on
on a
it?
different chair. No,
Yeah.
sensors more connected to your laptop, but it should feel your presence that you're working on it.
Mhm. Okay, so you could have something like an infrared camera
Yeah.
that
face
detects
thing.
your body heat And if it's getting colder, you left. Or,
Face. Touch the face.
okay, so a web camera could
Detect.
continuously analyze the video stream and look for some movement in front of the computer. You could also have something like this, which is why. So what happened to me the first time I got here, they gave me a key to one of the cubicles. I got in, I left my stuff, computer, phone, keys, backpack, coat, money, all of it, and then walked out to print a paper. And when I got in, the door got automatically locked, and there was no way for me to get back. Since then, I decided I would keep the key on such a thing, and this would be on my neck, so there's no way for me to forget it. Now, let's say if we used a computer system that uses cards for authentication. So when I sit, I plug it in, and it's there. And when I stand up, it's ejected because that's how the world works. This thing is only this long. If I get up, then the card is ejected, and this event acts as a signal for locking the workstation. Or let's say everybody, if we are in some kind of a chemical lab, and everybody must wear a suit, you could embed an RFID chip into the suits, or you could rely on the Bluetooth transmitter in my phone. So there are many things you can use as a presence sensor.
But in that case, the chances of getting hacked is easy. If somebody else gets this card or gets your jacket, then the chances are pretty high as compared
Still,
to.
it's on you, right? I mean, then it's your responsibility.
Then it's your responsibility.
Yeah.
It's on you, yes, plus you can always use multiple factors. Besides having to have this, it's also pin protected,
Yeah.
and the pin is only in my head. And again, we say pin, and when you say pin, this implies that it's a 4-digit number. But why not use one of these things? So, if I were in the shoes of the people in that group, I would remove this requirement from their policy. I would instead add another requirement to the engineers. All the software that you design must have a timeout clock and rely on some other method of deciding whether it's time to log the computer or not. Or you could do something else. For example, let's say you have physical security. To get into this room, you need to have this key. And to get out of this room, you must also have this key. Wouldn't it be great if the same key was used for the computer and the door? This way, even if I forgot it on the computer, I try to walk out,
You can't.
and I remember that, oh, I can't because I need that. So I go back, I take it out. In other words, we have completely, even if people forget,
Ecosystem.
even though people forget, and that's definitely the case, we designed the system's interface and workflow in such a way that we completely eliminate the scenario in which a person forgets their card. So it's easy to blame it on the human by writing rules, and you can have many, many rules which nobody bothers to read. And if nobody reads them, obviously nobody respects them. But on the other hand, you can take a different approach. You can take the humane way out. You can make it easy for the humans and make the software do the dirty work. Because computers are very good at doing things. They do them fast, they do them hundreds of times without getting tired, complaining, or asking for a sandwich or a 5-minute break. But humans are humans. They always forget, and for as long as there are people on this planet, there will be workstations left unlocked when they're unattended. You cannot kill all humans. That's not a way to solve this problem, but you can change their software. So that's another approach. It takes into account the fact that, well, we didn't discuss it here, but when you read about memory, you cannot not read about forgetting as well, because it's the other side of the coin. And forgetting is inevitable, so the only thing you need to do is add some kind of a reminder. Somebody could interpret this as, okay, I'm going to throw a little pop-up window on my computer every 5 minutes that says, don't forget to take your card out when you walk away. That's one way to solve the problem, but it's not a right way, because it's a distraction, and eventually people will develop a form of immunity against pop-ups. But this method, which I just described, completely eliminates that. Another thing that can happen to you as the user of a computerized system are phishing attacks. The first time I was exposed to this was when I didn't even have internet, and it was the context was as follows. I had a friend who studied in a school where teachers used computers to store files for tests, test results, and so on. And if you wanted to know what the test would be, you would have to get those files. The teachers knew about passwords, so they would password protect those files. And what my friend did is he observed what the teacher was doing. He saw which program they were using to enter the password. And then he made a simple program in Delphi, which looked exactly the same way. It had the same edit box with a password field. He would start that program by replacing the shortcut. The program would look identical, but when you press OK, it shows some error message or pretends that it crashes. But what it also does is it writes the password to some file. So you do that, you wait for the teacher to use the computer, then you go to that computer and you read the text file, and that's how you get your password. So in other words, they created something that looks exactly like the real thing. An unsuspecting user didn't notice that, so that's how they gave away their confidential, sensitive data. Today, this happens a lot with phishing when somebody sets up a domain that has a different name, but it looks like the real thing. And people do this all the time. They type their usernames and passwords into those fake sites, and this is how the bad guys get other people's credentials. And one solution to this problem is a so-called secure attention sequence, known as an SAS. Have you ever seen it?
Is it located on top of the browser or something there?
You mean the HTTPS? It's got a
No,
lock on
that's
it.
SSL.
No.
That is
That's
SSL.
completely different. It's not about browsers.
Okay.
So even though nobody said yes, you should have said yes. When you log onto any of the computers at the university, they say press Control Alt Delete.
Yeah.
You remember that? Why do you think they make you press Control Alt Delete? I mean, it's an extra step. It's 1, 2, 3 key presses. Can't I just type my username and password?
I think it was to generate the
Involves
Come
some
to that
kind of
password,
physical
yeah.
involvement of the user because of that.
Well, if I move the mouse and I see the things in front of me, the screensaver goes away, and then I just type my stuff. Why not do it that way? Can you generate another guess? Okay, I will tell you where this comes from. In Windows, there is another desktop called the system desktop, besides the user one. The system desktop is the one where the authentication screen resides. When you log on username and password, all of that stuff is rendered on the system desktop. And in Windows 2000 and XP, whenever you see the authentication screen, all of that stuff is handled by a component called Gina. It's a DLL, a library that exports several functions that are used for authenticating users. In Windows Vista and in Windows 7 and in Windows 8, there is no Gina DLL, there is something else. It's called a credential provider. This thing runs in the background such that whenever you press Ctrl-Alt-Delete, this key press is first received by this component or this one. And when you do that, it gives you that dialog for locking, unlocking, logging off, logging on. If I were a bad guy, I could make a Windows program that looks exactly like the standard authentication screen, hide the system bar, run my program in full screen, and then just wait. I would wait for people to come to the computer, move the mouse to remove the screensaver, and then they see the authentication screen, they type username, password, press OK, I can save that to a file, and as a bonus, I can then actually authenticate them into the system using the credentials they just gave me, such that they won't suspect that something was fishy in the middle. Which is why I told you that the Ctrl-Alt-Delete sequence is always received by this component first, and then transmitted to some other processes. So this means that if you press Ctrl-Alt-Delete, you are definitely looking at the real thing, not something else. If you are running a program that looks like the authentication screen, but it's not the authentication screen, when you press